All right, folks, here is an example of a hollow sphere rolling down an incline without slipping. Again, it is a hollow sphere, not a solid sphere, so pay attention to your coefficient of a moment of inertia. So with part A, it asks you to derive an expression for the linear speed at the bottom of the ramp in terms of G, L, and theta as dictated by the diagram as you see on the screen there. So the first thing we want to do is to set up conservation energy because mechanical energy has to be conserved. So the first statement I have is MEI equals MEF. From there, you just have to identify the energy that's present during the motion. So initially, it has a PE due to gravity, which can be expressed as PEI, and that has to equal to KE linear and KErot because the object is rolling as it's moving down the ramp. So it has two types of KE. From there, you can break up PEI into MGH by definition, and then KE linear is just 1/2 mv square, and KErot is just 1/2 I omega square. And then you can go ahead and expand I in terms of CMR. C stands for the coefficient of moment of inertia. In this particular case, the shape is a hollow sphere. So if you have your values memorized, it is 2/3. And then we can replace omega with V over R. Again, that comes from just the relationship between linear and rotational motion. And then if you go ahead and distribute the square to the V and the R on the right term here, you notice that the R square, again, and the R square here will cancel out. And that'll just leave you with 1/2 CV square. And you notice here, mass here appears in each term, so that does get canceled out. So in the next statement here, where my arrow is, you don't see any mass involved there. And then from here, you notice that it has a 1/2 V square in common. This term has a 1/2 V square. This also has a 1/2 V square. So we can go ahead and factor that out, and then that will look like this in the next line. Again, good habits, you would indicate that this is a 1, because once you factor everything out, that is just a 1. And then once you have factor out the 1/2 V square here, that's just a C as I indicated in the parentheses. And from there, we can just do basic algebra manipulation to solve for V, because the question did ask us to prove V in terms of G, L, and theta. Manipulating it, you would divide both sides by 1 plus C in parentheses and multiply both sides by 2. Hence, the 2 is in the numerator. And then the denominator here is just 1 plus C. And then to solve for V, we got to square root the whole entire left side of the function. So it looks like this. Okay, so it'd be radical 2GH over 1 plus C. And this is a typical form that you can use for any rolling object, for a solid sphere, hollow sphere, disc, ring. You just have to know your I value coefficient, the moment of inertia, and then you can just substitute it here, and that'll always work out as long as you know H. But in this case, we don't want to stop there because it wants us to derive an expression in terms of G, L, and theta. And as you can see here in the diagram, theta is given, H is given, L is given. So it just wants us to take a little step farther. But typically, you can stop here where I have it highlighted in yellow. So we can go ahead and replace the coefficient of a hollow sphere with 2/3, as you should know. And then the numerator hasn't changed. And then from there, we almost have it where we need to be. Combined like term, this is a 1. To add the fractions here in the denominator, you have to do a common denominator. So the 1 just turns in 3/3, which reduces down to 1. Your common denominator is going to be 3. So 3 plus 2 in the numerator, that's 5. So that's going to look like this right here. Again, the numerator hasn't changed, which is 2GH. The bottom turns into a 5 because 3 plus 2 is 5. The common denominator here is 3, so that's going to be a 3. And then if you divide by a fraction, your algebra skill should tell you to multiply with the inverse of 5/3, which is 3/5. So therefore, 3 times 2 is 6, which I have here, and then the 5 remains in the denominator. But again, we're a little closer, but we're not to where we need to go. We still have to get rid of H. We have G. It doesn't want it in terms of H. So from basic geometry, if you look at the diagram on the bottom left of the screen here, sine of theta by definition is opposite, which in this case is H, the height of the ramp, over hypotenuse, which is L. And we can just go ahead and solve for H since it doesn't want it in terms of H. So to solve for H, we multiply both sides by L. So therefore, H is L sine theta. And we can just go ahead and substitute that in here. Where my cursor is, H can be replaced with L sine theta. And that will be your final result. Okay. For part B, it asks us to find the magnitude of the linear acceleration, ACM, and that can be expressed as 3/5 g sine theta. That's a common function for this particular type of shape rolling down a ramp. So the first strategy you can use is common form from your kinematics day. So, but you know that VF square from the previous part, again, this is VF square, would be 6/5 GL sine theta. And VI is 0 because it's released from rest, and then 2A. And here your horizontal displacement, aka the length of the ramp, is indicated by L in the diagram. So I just went ahead and replaced delta X with L, which is a straightforward substitution there. And then as you notice here, this term has an L, this term has an L. So we can go ahead and cancel that out. So the next term that I have here is just 6/5 g sine theta, which is equal to 2A. And again, to solve for A, we would just divide both sides by 2. So that would leave us with this. It would just be 6/10 because 5 times 2 is 10. And again, you can reduce 6/10 down to this particular statement, 3/5 g sine theta. And this is the acceleration down the ramp for a hollow sphere, as long as you know the slope, aka the angle of the ramp. Okay. The second strategy that you can apply if you want to would just be to apply torque. Torque equals I alpha, or equals F times your lever arm. In this case, your lever arm would just be R. So your first strategy would be to use F of K as I indicated here in the diagram. Friction is going to be pointing upslope as the ramp, as the hollow sphere goes downslope, because that's going to cause a clockwise rotation. So F of friction is what's going to cause your torque. So if you can just replace it with this particular statement. Again, the moment of inertia for the hollow sphere is 2/3 mr squared, given that the pivot right now is at the center of mass, which is where my cursor is, right through the center of the hollow sphere. And then we can replace again A with A over R, or excuse me, alpha with A over R. And then instead of F, we can substitute F for the force of friction, which is what's causing the torque, aka rotation for this particular hollow sphere as it goes down the ramp. And we times it by the moment of arm, or the lever arm, which is R, measured from the pivot, which is at the center of mass, down to where the force of friction is on the incline. And you just do basic manipulation. Again, this R can be moved down there. That'll make it R squared. That R squared is going to cancel out with the R squared here. So essentially that leaves you with the next statement, which is 2/3 MA. And there's no R in that statement because all the R cancels out. And you can go ahead and simplify for A. And this is what A is going to look like. Okay. But then we also can go ahead and set up Newton's second law. We don't know what Ffric is, but we can go ahead and set up Newton's second law. And that's going to leave us with this statement. As the ball goes down the ramp, there's F of Gx acting on it, minus the opposing force, which is F of friction in this case, and that equals to MA. And we want to go ahead and expand F of Gx to mg sine theta, because that's what F of Gx equals to in this particular diagram. No funky stuff here. And then, again, in the statement up here, we have A is equal to 3 Ffric over 2m. We don't know what the F of Ffric is, so we can go ahead and isolate for F of Ffric in this particular statement. And we can just substitute. So moving MA to the left side, that becomes a minus. Moving the negative Ffric to the right side, that becomes positive. So therefore, we have a statement for Ffric. We can substitute that in. So it's look like this. So again, I want to take this line and move it down here. The 3 in the front is right there. Again, I'll use parentheses when I substitute. And instead of Ffric, I can replace Ffric with mg sine theta minus ma. As you can see where my cursor is at the moment, the denominator hasn't changed, which is 2m. I'll leave that as is. But you also notice here, there's an m there, there's an m there in the numerator. So both the numerator terms here have an m. You can factor that out. And once you factor that out, that m is going to cancel with the m here. And that's going to leave us with this particular statement. And again, to solve for A, you would have to just do basic algebra. So I'll go ahead and multiply both sides by 2 just to get that to look like combine like terms. And then you have a 2a on this side, you have a negative 3a on that side. Combining like terms will yield 5a equals 3g sine theta. And solve for a, again, we just divide both sides by 5, which is going to yield the same statement it is on the left side here, 3/5 g sine theta. So that's the second alternative method. The third one, which is up to you, I kind of like if you don't like the first method. The second method I would avoid. It does take a little bit of time. The third approach here is I like shifting my pivot to where the point of contact is on the surface of the ramp. And that point right here along the ramp, as it rolls down, is instantaneously at rest. So I don't have to worry about anything. But once I shift the pivot, though, instead of center of mass, my pivot will be down there. I do have to apply the parallel axis theorem, which gives me I nu. And I nu, aka the parallel axis theorem, is given by this function, ICM plus MD squared, where D stands for the distance shifted. In this case, it went from the center of mass to where the surface of the ramp is, which is the distance of R. So if you do that correctly, it's pretty straightforward. ICM for a hollow sphere is 2/3 mr squared plus m, which is the function there. And then again, I can replace D, the distance shifted, by R, because it did shift a distance of R from the center of the hollow sphere to the surface of the incline. It's the distance of R. And then I can go ahead and just replace alpha with A over R. And then the force that's going to cause the rotation is going to be F of Gx. F of K in this case would cause no rotation, because since I shifted my pivot down here, where the surface is, F of Ffric run right through the axis of rotation. So that causes no torque. But what does cause torque, though, is F of Gx, because I have a distance R, and F of Gx is indeed perpendicular to R. So that's actually going to cause the rotation. Again, this is a different perspective look at it. So instead of Ffric, I'm actually going to apply F of Gx, which I like, because I know what F of Gx is equal to from previous units. And then if you do basic math, common denominator here is going to be a 3 to turn mr squared into the same common denominator. You multiply top and bottom by 3. So 2 plus 3, and then the denominator is 3. Again, nothing changes here, nothing changes here. So just one step at a time. So if you add the numerator, 2 plus 3 is 5. You get there, common denominator is 3, so that gives that. And then I went ahead and replaced F of Gx. By now, you should know F of Gx is mg sine theta, and there's your level arm, which is R. I just carry down. Again, you notice here's an R, but if you move the R to the left side of the function, it will turn the R here into a square, which will cancel out the numerator R squared here. And it's going to leave us with this statement once again. And then to solve for A, you can go ahead and multiply by 3 over 5, which will cancel with 5 over 3. And that will give us this particular result. And that, again, shows you that it doesn't matter which approach you take, you get the same answer. I particularly like the first one. If your kinematics is strong, assuming you can get VF using part A. And if you don't, you can apply torque. And I like using the parallel axis theorem because it is a little quicker than the middle section here. So make a choice. As for part C asks you to find the Ffric and show that it can be expressed as 2/3 ma. This is pretty light work because you can apply just torque. Again, traditionally, the frictional force is what's causing the object to quote unquote roll down the ramp. So you can just go ahead and stick with that. But if you do use Ffric, the axis rotation is right through the center. And because it is through the center, the distance away from Ffric, which is explained in the previous part, is along the surface of the incline pointing upslope. But again, I don't need to use I nu, I need to use ICM. And ICM for hollow sphere is 2/3 mr squared, changing alpha into A over R. And again, you have to identify what's the force that's causing the torque or the rotation. In this particular strategy, it is the frictional force, since I'm using ICM for the hollow sphere. So again, I replace F with Ffric, the R remains the same. And again, once again, this R, and this R squared will cancel out. It's just basic algebra. And it's going to leave you with the statement Ffric is equal to 2/3 ma. So this is pretty useful. Why? Because once you know A, you can find the frictional force present in the problem. Okay, so there's your statement. That's a quick proof. The second strategy to prove it, which I don't prefer, it is a little quicker, but you can just apply Newton's second law, which is sigma F equals ma. In this case, as it rolls down, there's F of Gx linearly and there's F of K linearly. The sum of that, or the difference of that, in this case, would be ma. And if you substitute for what you know, F Gx is mg sine theta, Ffric is just ma, but you don't know what A is. So again, we're just solving for Ffric here, and we're trying to prove a statement. So if you isolate for Ffric, and go ahead and isolate for that, because that's what the statement is looking for. Ma, move it to the left side, becomes negative. Again, the negative Ffric moves to the right side, becomes positive, changing the sign there. But from the previous statement, we know that the acceleration for a hollow sphere down an incline without slipping is 3/5 g sine theta. And we just do a quick substitution here. So manipulating this one though, you do have to manipulate for g sine theta. So this is a quick trick. Why? Because again, we don't want any sine theta in our statement because the question is asking us to prove that Ffric is indeed 2/3 MA. So you have to identify what you need to get rid of. In this case, I want to get rid of sine theta. Why? Because the statement has no theta in it. Changing A equals 3/5 g sine theta, I can go ahead and multiply both sides by 5/3, and then I will just leave the g there because again, I'm just trying to get g sine theta to be by itself. And then from there, you can just do a quick substitution into the statement here that I have drawn the arrow for. So instead of g sine theta, we can just replace g sine theta with 5/3a minus ma Ffric. And then again, basic math here, you have 5ma/3 minus ma. You need a common denominator. So the common denominator would be 3 again. So multiplying top by 3, dividing the bottom by 3. Again, that reduces down to 1. So it'll be 5ma minus 3ma over a common denominator of 3. And that's going to leave us with 2/3 ma, which is equal to Ffric. Again, which is the same statement that I have here for you. So I prefer the left side. The right side is an alternative for you to kind of see where you can apply previous answers if you choose to. And then part D and E, I'll do that on the same slide here. It said what's the minimum coefficient of friction in terms of the angle. Again, bust out the definition of coefficient of friction. That would be the Ffric over f of n. From your previous days on the diagram here, you know the f of n is normal to the inclined surface and f of gy is pointing in the opposite direction as f of n. Again, there's no funky forces here, so these two forces are equal to each other. So Fn must equal to f of gy, and then by now you should know f of n is equal to f of gy, but f of gy by definition is mg cosine theta. And again, the answer to Ffric from the previous part C is carried over here. So Ffric is 2/3 ma. So I substituted Ffric for 2/3 ma, and then f of n, which is f of gy, which is mg cosine theta, is placed there. And then the m cancels out here. As you can see there, there's a numerator m, there's the m in the denominator, so that cancels out. So that's going to leave us with that. Okay. And then from here, you can replace A with 3/5 g sine theta from the previous part. And then the 3 here is going to cancel out. And that's going to leave us with this particular statement. Again, the 3 cancels out, leaves us a 2/5, which you see here in this next line. The g also cancels out. So you won't see it here, but sine and cosine stays the same. But sine and cosine reduce down to tan. And then what I did here, since the question asked for minimum, I just changed the equal sign to greater than or equal to symbol. Technicality stuff, it doesn't really matter as long as you know what's being asked of you. In this case, the minimum, so anything greater than that works. So sine over cosine is tangent. So really the expression that you can find the coefficient of friction is 2/5 tan theta, whatever theta is, okay? And then here's part E. Part E asks us to derive an expression for pretty much KE rotational in terms of mg and h. Show that is 2/5 mgh. So I would just start with the expression for KErot. KErot is 1/2 I omega square, and then I cm for hollow sphere again is 2/3 mr square. Get rid of omega and replace that with v over r, but every term has to get squared, so it turns into v squared over r squared. And again, the r squared here is going to cancel out. The half, the denominator 2 and the 2 in the numerator is going to cancel out. So that's going to leave us with just 1/3 mv squared. But you already know v from part A. Part A, I derive a general expression for you, which is just 2gh over 1 plus c, where c is your coefficient of moment of inertia. In this case, it would be 2/3 for a hollow sphere at the center of mass. So if we substitute that, where c here is 2/3, again, I just, instead of v squared here, I substitute all this right here. So there's a 2gh over 1 plus c, but c again is 2/3. Basic algebra again, find common denominator. So the common denominator for 1 and 2/3 is 3. So the 1 here turns into 3/3, and then 3 plus 2 is 5. The denominator is 3. So that's going to look like this again. But anytime you divide by a fraction, you have to multiply by the reciprocal. So the common denominator here is 3, but we got to flip it. So 3 times 2 is 6, and then 3 plus 2 is just 5, which is right there. And if if you're awake and thinking, uh, by this point, you hopefully see that the 6 and the 3 here will cancel out, which will leave us with just 2 fits, which is just the expression that it asks for. Okay, so I hope this helps in terms of navigating functions, deriving stuff, using stuff that you derived in previous parts to apply it to the next parts. All right, other than that, don't be whack and stay nerdy. Thank you.